This lesson deals with supplemental problem 319. You can find this problem in the ECE302 ebook in the Chapter 3 Supplemental Problems, starting on page 28. Let's revisit the power supply design that we did in supplemental problem 215. This time I want to have you design a transistor-regulated power supply for this Panasonic stereo model RX FT560, given the following. If you recall that the stereo with a 12-volt power supply connected in place of its batteries drew a maximum current of 1.4 amps and a minimum current of 200 milliamps. We used a Zener diode regulator, as we saw in Chapter 2, pages 76 to 79, and we saw that there were severe wattage problems with the resistor, and also we had a very large capacitor. Let's use a transistor regulator like the one we used in supplemental problem 318, and with a 13-volt Zener diode. Here's our full-wave rectified power supply with a smoothing capacitor. In place of the load now, we're going to put this transistor regulator we had in the previous supplemental problem with our stereo as a load. We drew this a little bit differently. And there's a couple different ways of drawing this particular regulator. I want to show you those two in these two supplemental problems. And then our load effectively is going from this resistance to this resistance. Suppose that the minimum current in the Zener diode is 20 milliamps, and that the voltage here, the average voltage, is equal to 18 volts. I'm doing that because I have a 13-volt Zener diode here, and I need to be larger than that to keep this Zener turned on. Pick the largest value of R sub Z for the range of R0 shown, assuming that beta F is 50, VBE on is about 1 volt, and transistor Q1 is active. Next, using your value of R sub Z, calculate the average current for I sub L. R sub L seen by C sub L in the bridge rectifier is the ratio of V sub L to I sub L. Pick the value of C sub L such that the desired ripple is 4 volts peak to peak or less. We'll have 18 volts for V sub L plus 2 volts minus 2 volts. We'll be able to keep the Zener diode turned on. Assuming the VD on in the bridge rectifier is 1 volt and the wall outlet is 120 volts RMS, can you pick the turns ratio of the transformer? Next, test your design with PSpice. Assume for the diodes that I sub S is 997 picoamps and 8 is 1.67, in other words a 1N4001 diode. And the Zener diode has a breakover voltage of 13 volts at a current of 20 milliamps. And for the BJT, the beta F is equal to 50. For a sine wave input and R0 equal to 8.57 ohms, can you plot V sub L and V out versus time for 4 cycles of V sub S? And then repeat that for the 60 ohm load. For R0 equal to 8.57 ohms, find the average power dissipated in one diode in the bridge rectifier, the Zener diode, R sub Z, and Q1. Then repeat that for the 60 ohm load. As we showed previously from our 12-volt data, the maximum resistor is when we have the minimum load current of 200 milliamps, and that's effectively a resistance of 60 ohms. And then for the 1.4 amps, it looks like 8.57 ohms. Let's put in the active model for the transistor and the Zener in the Zener region. Here's V sub L and I sub L. Here is my base, collector, and emitter. Between the base and emitter, I've got a VBE on of 1 volt, a current source between the collector and the emitter of beta FIB or 50 I sub B, my Zener voltage of 13 back to ground, and then my resistor R sub Z with a current I sub RZ in it. And then I have my stereo, which I want to have 12 volts across it, and the current going into it is 51 I sub B. Let's take a look at the worst case, and that's when you have the most current in the load and the least current in the Zener diode. It would be 20 milliamps, and this would be 1.4 amps. If we can satisfy these two conditions, then as we back off on this number and put more current in here, we'll be able to operate the radio and also keep the Zener going. Current in here is going to be 1.4 amps. Again, it's 12 volts divided by the 8.57 ohms. That's equal to 51 IB, I sub B plus 50 I sub B. We can solve for I sub B as 1.4 amps divided by 51, or 27.45 milliamps. I sub RZ is the current entering the node. What's leaving is the base current and the Zener current. The base current is 27.45 milliamps, and we're letting the Zener current be the minimum of 20 milliamps. It's 47.45 milliamps. This resistor then would be the voltage across it divided by the current. That's 18 volts minus 13 divided by 47.45 milliamps. And that's 105 ohms. The nearest standard resistor is 100 ohms. The current I sub L is equal to 50 I sub B plus I sub RZ, 50 times I sub B plus I sub RZ, and we get 1.42 amps. A little bit more than is going into the load. We can now solve for R sub L. This is the resistance effectively seen by the capacitor C sub L. as a ratio of V sub L to I sub L, which was 18 volts, the average voltage, and then the average current of 1.42 amps. That's 12.68 ohms. Our ripple formula is V sub L max over twice F R sub L C sub L. And V sub L is V sub S, the secondary voltage, minus 2 diode drops. And then we had the maximum value of V sub L is going to be the average value plus half the ripple. And this was 4 volts divided by 2, so 20. We can now solve for C sub L. Bring that over here, bring that over here. V sub L max over twice F R sub L and the ripple voltage. 20 volts, twice 60 hertz, 12.68 ohms, and then 4 volts peak to peak. We get 3,286 microfarads. And the nearest standard capacitor is 3,300 microfarads at a rating of 35 volts. Our voltage can be around 18 volts, going up to 20, so this will be more than enough. Now we found that V sub L max was 20 volts, and that's going to be equal to V sub S max minus the 2 diode drops. We could solve for V sub S max. That's going to be equal to 20 plus 2, or 22. The peak on the primary is going to be 120 volts RMS times the square root of 2. That's about 170. And then our secondary, the maximum is going to be 22 volts. That ratio is 7.71. I looked online at a Hammond catalog which makes transformers, and the nearest transformer I could find was with a turns ratio of 7.67, with a secondary current of 1.6 amps RMS, or 2.26 amps peak, and of course our current's much smaller than this, so we'll be okay. Here's our initial design. Got a transformer with a turns ratio of n to 1, 4 diodes, C sub L, and effectively some resistance looking back here with our regulator, which has an R sub Z, a D sub Z, and a Q1, and eventually our radio. Here's my PSpice file. So I've got a title. Replace the transformer by a voltage source between nodes 1 and 3 of a sine wave with an average value of 0, and then a peak value of 120 volts RMS times the square root of 2, now divided by 7.67, our turns ratio of our actual transformer, and then a 60 hertz frequency. Here's my 4 diodes, my capacitor rounded to 3,300 microfarads, my resistor R sub Z of 100 ohms, my zener, the transistor between the collector base emitter. Let me use a 2N3055 power BJT from our last supplemental problem for now. We'll still need to verify that it can handle the power delivered to the circuit. And my load being 8.57 ohms. The model for my diode is the 1N4001. My zener with 13 volts and 20 milliamps. The beta for my transistor of 50. And then I want to do 4 cycles, so 1 over 60 is 16.66. Multiply that by 4, and then divide that by 200. Start at 0 and make the sealing step the same as the print step. Take a look at the output. Apply the 2 nodes. The voltage across the capacitor at node 2. You see I've got a ripple here. And then the output voltage. And the output voltage is around 12 volts. I have an average value on the output voltage by the capacitor of 18.85 volts, a peak of 20.27, and a minimum of 17.427. How does that compare to our specs? Well, the ripple is the difference of these two. And that's 2.84 volts. I was shooting for 4. So that's better than what I expected. The turn-on voltage for VBE is the zener voltage minus the output voltage. And that's about 1 volt, 0.95. On the previous page, we had a formula that V sub L was equal to V sub S minus 2 VD-on. We could solve that equation for VD-on. It would be V sub S maximum, which is 22.13, as we calculated above, and then minus the peak value of V sub L, which is 20.27, and then dividing by 2. We get a turn-on voltage for the diode of 0.93 volts. Let's repeat the last simulation for the load of 60 ohms. You can see my ripple has decreased by quite a bit. It's only 582 millivolts peak to peak, and the average is 20.07 across the capacitor, but my output voltage is still about 12 volts. The worst case was the previous one to satisfy. Let's go back to that previous simulation. I forgot to mark down here, but this is for the case of 8.57 ohms. I want to run this where I'm in steady state, so I'm going to start not at 0, but at 1 period later, 16.66 milliseconds. I'm still going to go out to the value of 66.6. Now the difference of these two divided by 200 is about 250 microseconds. Then if I go for 1 period after my start, that would give me the average value. And that's around 33.32 milliseconds. So I marked on here average value of the power in the transistor, the diode in the bridge rectifier, the zener diode, and that resistor that we had feeding the zener. In the bridge rectifier, my average power dissipated is 711 milliwatts. For the zener, 413 milliwatts. For the resistor, 359 milliwatts. And for the transistor, 9.5 watts. Repeating the simulation for 60 ohms. I'm going to mark the power dissipated in the Zener diode, the transistor, the resistor R sub Z, and one of the diodes in the bridge rectifier. And the values are down here. Here's the diode in the bridge rectifier. It's 126 milliwatts. The Zener diode has gone up to 865 milliwatts. Power dissipated in the resistor has also gone up to 495 milliwatts. And the power in the transistor has gone down to 1.57 watts. Of these two cases, let's pick the bigger of the two for our selection of the components. For our Zener diode, let's pick a 1 watt Zener. I did some searching and found that it was a 1N4743 Zener diode that was rated at 1 watt. And I would pick R sub Z to be maybe a 1 watt resistor. And then we could use the 2N3055 we did in supplemental problem 318, which can have a maximum collector current of 15 amps and a power dissipated of 115 watts at room temperature. As we discussed before, we probably should add a series resistor to the transformer secondary to minimize the surge currents. Suppose we add a current limiter to protect the radio from a short circuit at the output. This is based on a magazine article in the magazine entitled Hands-on Electronics in Volume 2, Number 2, entitled Designing Practical DC Power Supplies by Joseph Carr. He suggests adding a transistor and a resistor to this regulator. It does the following. If the current in here is small enough so we don't create a voltage big enough to forward bias this junction, then this is cut off and our circuit just delivers current to the load. If the current starts to increase, creates a drop here of say 0.7, then this transistor can go active and begin to pull current away from the base from R sub Z. This will stop any further increase in current flowing. When Q2 goes active, the voltage across the collector emitter of Q2 is the difference between the Zener voltage and now the new output voltage, because this is a current source. Suppose we want to limit the current to 2 amps. Then this resistor would be 0.7 volts, if that's the turn-on voltage for Q2, divided by 2 amps. You need a resistor about 0.35 ohms. Since Q2 is pulling a small base current from Q1 into its collector, we could use any low-power NPN transistor for Q2, for example a 2N3904. Lastly, it's always a good idea to add a fuse whenever you're directly connected to the wall outlet, because it's an enormous source of energy, and you don't know what's going to happen in that radio, the load, or the person handling it. As we've shown the transformer on the previous page, the value of N is the ratio of the secondary to the primary. We could solve for the primary current by taking the secondary current and dividing it by N, and the maximum secondary current would be the maximum diode current. And our turns ratio was 7.67. If we decide to limit the current to 6 amps, then we could solve for the fuse current. In this case, it'd be 782 milliamps. And the nearest standard fuse size is a 3/4 amp fuse. I should make one last comment. A current limiter can respond much faster than a fuse. Typically, a current limiter is going to respond in hundreds of microseconds, whereas a fuse is in hundreds of milliseconds. And this is supplemental problem 319.